sp2 and sp3.
Linear, trigonal, planar, and tetrahedral.
Right. And then a good question came up yesterday. Does it have to be these all the time whenever you have those shapes? And Jason had a good question on this, and let's try to tweak this out and see if this makes sense. All right, so let's do ammonia for a moment. If you have a 1s2, 2s2, 2p, go ahead. 2p, 3. All right. So you could imagine that there are three not open, but three possible locations that additional 3 electrons could go into the 2p sublevel. So if you have an orbital diagram, something like this, it makes sense that you could fit 1 electron from one hydrogen, 1 electron from a second, and 1 electron from a third. You don't have to have hybridization there. So just because this is trigonal pyramidal molecular geometry doesn't mean that there is some weird hybridization occurring. So what do you do? How do you know when to do hybridization versus not? Arguably, if you did something like CH4, all right, so that's tetrahedral, we could say, as a guess, maybe it's sp3. 1s2, 2s2, go ahead, 2p, 2. So we have the same similar notation, except for the fact that it only looks like we can form how many bonds with carbon? Yeah, this is carbon. So how many bonds could we form with carbon? 2. It looks like 2. I like that. I've never told you, and I appreciate your deeper level thinking here. Why can we not stick 2 there into this 2p sublevel?
There's nothing for it to bond with.
Yeah, you're not sharing any covalency. You have no electron density of carbon to share with those incoming electrons. So you're not just going to take 2 electrons from some atom, dump them into a new atom, and say, oh, that was partly carbons to begin with. So you have to have carbon character there. So in essence, we've said it looks like this electron can be promoted to a higher energy level. We can do that because this is still the second energy level, So that would have been a general chemistry and honors chem 1 explanation. The real explanation is you're taking the s atomic orbital and hybridizing it across 3 degenerate p orbitals. So now you create how many hybridized sp3 orbitals? If you have 1 atomic plus 3 atomic, how many hybridized orbitals did you form? 4. And that's given simply by just counting these. 1 plus 3 is 4, 1 plus 2 is 3, and 1 plus 1 is 2, right? So that tells you how many hybridized orbitals you formed. So it does make sense here that we need hybridization in order for 4 different hydrogen atoms to come in and bond to the sp3 hybridized orbitals of carbon. So let's kind of break this apart for a moment. If you have ammonia, and you have the molecular geometry, something like this, this would be tetrahedral electron pair geometry, however, a trigonal pyramidal molecular geometry. Notice that the unhybridized p atomic orbital of nitrogen, right? So we're talking 1, 2, 3 of those. So here they are. I'll just draw them like this, or partials of those p's. Interact with the unhybridized atomic orbital of hydrogen, right? And you can just draw that as a round sphere because now these are 1s electrons that are going into, or interacting with, rather, the atomic orbital of 2p of nitrogen. So you see some overlap here. I'll just kind of shade it in. Those overlapping regions create a covalent bond. Now, based on the symmetry of the molecule alone, let's do no electronegativity calculations, although we could, like from yesterday, and figure out the percent ionic character. Based on symmetry alone, is this polar or non-polar? It's polar. Looks like, where's the electron density going? Towards the nitrogen or away from the nitrogen? So who's more electronegative?
Towards nitrogen.
Towards nitrogen. So notice too that there's an additional lone pair of electrons here, so slightly negative versus the slightly positive. Anytime you have a separation of charge, new word for today, we're going to use this, bring it down here. This is called a dipole. You might have heard that in passing, but legitimately di meaning 2, pole meaning regions. 2 regions where the charge distribution has isolated itself more or less to. That's a dipole molecule. That's a dipole moment. Okay. There's a calculation. You don't need to know it. In essence, what it's looking at, so you can write it down. We're not going to do anything with it. This is a debye. It's a unit associated with the magnitude of the dipole, meaning the greater the magnitude, the greater the dipole. Now you have a more polar molecule. If you increase the polarity of this molecule, so if you take this electron density and shift it even further and further and further away, do you start creating an ionic compound? Think about that carefully. You take that electron density and you shift it further and further and further away. Are you now generating an ionic compound?
Yes.
Yeah, because you're almost completely removing the electron density. So that's in essence when we said that there's some sort of energy diagram. We've used this quite a bit. It relates to Coulomb's law. We could talk about the stability of an electron on an atom. We could also talk about the stability of two atoms binding together. So if we call this the lowest potential energy state, is that the region of maximum stability? Lowest potential energy, maximum stability? Yeah, absolutely. And as we increase in energy, if we get to the value of 0, something unique has happened where if we're taking, let's just draw the electron density of one atom and the electron density of another atom, in essence, we're ripping the portion of the electron density off and we're completely ionizing two atoms almost completely. So almost creating a permanent positive charge and a permanently negative charge. Whereas here, we might have those two atoms, I should have drawn that a little more carefully, that are doing some covalent overlap, where we have a slightly positive and have a slightly negative. And if you keep pushing those atoms in even more, that potential energy goes up very, very high. Take a guess why. So this is pulling the atoms so far apart. Like think of it as a rubber band. You have to apply energy to keep pulling and pulling and pulling, right? And a whole lot of energy and then it snaps. And once it snaps, perfect. You have two separate pieces. This would be like just hold the rubber band in your hand. Don't pull on it at all. What's its normal elastic position of equilibrium, right? This would be taking the rubber band and trying to push and push and push, or more like a spring, taking a spring and push, 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 keep pushing it together. Why does the energy skyrocket, in essence, become exponential when you move two atoms very, very close to each other?
There's no breaking point.
Keep going.
It's like they can only get closer and closer, which becomes harder and harder.
What happens when two atoms move almost identically into becoming one atom? What process do you call that? Nuclear fission? Fission splitting, fusion combining things together. So we need the almost enormous amount of pressure to do that and heat, which would be comparable to a star system in essence. So you have the protons of one interacting with the protons on the other. Those are going to begin to repel. And then you have this huge amount of electron density interacting with a huge amount of electron density, and those also are going to repel additionally. So when we talk about this kind of dipole moment, we're in essence keeping this in the back of our brain. What is the optimal distance? That's the value of r. This x-axis here is r, the distance away from between two atoms in a nuclear axis. So that's the magnitude of the distance, and this is in essence just the charge. So this is the bonding atomic radius, and this is charge distribution. The greater the charge, the greater the dipole moment, or the greater the distance, or separation of charge, the greater the dipole moment.
We don't need to know that, right?
You're not going to do anything with this calculation, but that's the theory of how dipole moments are generated. So for you, if you just look at a separation of charge, you can call that a dipole. The greater the separation of charge, the greater the dipole moment. In essence, making this a polar molecule, right? Okay. All right, that was yesterday. Today, intermolecular forces, a little bit of molecular orbitals, and if we have time, some bonding enthalpy type scenarios as well. Okay, IMFs is what you've called them before. I never call them that, but I'll call them that. Intermolecular force. What does that imply? Just the language of it.
Forces within the molecule.
Yep, I like that. We'll tweak it slightly. The ER here is between two molecules. So intra-molecular interactions are bonds that occur within a molecule, like covalent or electrostatic forces of attraction for ionic compounds. Intermolecular forces are those bonds that occur between two different molecules. They could be identical molecules or they could be non-identical molecules. It doesn't matter, but there are a handful of those that we can generate. Kind of the first one, I'll list them out here, and then I'll give an example of each one. There's dipole-dipole. There's something called hydrogen bonding. You guys you've seen this before. I almost can guarantee it. Depending on which teacher, which class, you might have called them London dispersion. Or for me, I'm going to call them instantaneous. And induced. Those would be the two ones that we look at. There are other types, and we're not going to discuss them in depth, so I'm going to just write them. There's things that are called metallic. We'll eventually get to a point where we look at the crystalline structure of ionic compounds and do a little bit of math with those, so we can have interactions between molecules that create an ionic compound with repeating patterns over and over and over again. And then there's a few other different types related to the metallic nature of structures like diamond and etc. Okay. All right. So let's start here. Dipole-dipole interactions. The simplest version I can think of would be this. Let's consider hydrochloric acid or hydrogen chloride. The electron density will shift towards the chlorine atom, making it slightly negative and making it slightly positive, because the electronegativity value of chlorine is so large that it pulls that electron density of hydrogen closer to itself to stabilize the valence shell of chlorine, right? That's due to the effective nuclear charge of chlorine altogether. A high effective nuclear charge will pull those valence electrons closer towards itself. That still makes this definitely slightly positive, and this one definitely still slightly negative. So this would be a pure solution, if you will, of hydrochloric acid, or maybe just hydrogen chloride gas might be a better way to look at that. Cool that system down enough, allow some bonds to begin to occur, and you'll start to create some bonding nature between this chlorine and this hydrogen atom. Now, is that a strong bond? That's dependent upon which type of force we're talking about. So, add in one more here. So you can put this underneath if you want to. Ion-dipole interactions. That'll help us here. In terms of the relative strengths of these are pretty stinking weak, but collectively, very strong. So if you have millions and billions of these occurring within a solution, collectively, it might be a pretty strong intermolecular force network. This stabilizes your DNA. I'll show you that in a second. So relatively pretty strong, and these are pretty strong as well. So in terms of strength, we'd have to look at the empirical data and jogging the memory here. I think number one, number two, arguably number two-ish as well in terms of strength, or maybe even one. So these, let's just say here and here are your top three. These all fall below that in terms of relative strengths. Okay, so is this okay? Would we ever have a situation where the chlorine atoms begin to interact like this? So this occur? No, because this is slightly negative. They want to repel each other, and so you don't have that occurring. So notice that what we have a dipole moment that's been created in this hydrogen chloride molecule, where the end of the dipole, the negative side of it, is interacting with the positive portion here. So you have a dipole of one molecule interacting with the dipole of another molecule. A good example of that. Okay. All right, let's do hydrogen bond. A hydrogen bond is just a certain type of dipole-dipole molecule. Consider water. If you draw them like this, then we'll end up bonding them together. So if you don't distort anything here. Okay. We shift the electron density towards the oxygen because there's lone pairs here, right? So this becomes slightly negative, and this area becomes slightly positive. That's true on all the other oxygens as well. Whenever you have a dipole moment created, and this is slightly positive, you have a dipole-dipole interaction. In essence, this strong, let me go ahead and do it this way. I have to sneeze so bad, it's not coming out. I've been fighting it for like 40 seconds. Give me a moment. It's really messing with my head. It is. Come on! Somebody hit me in the nose.
Look at the light.
How long do I have to look? Look for a while?
Did you even consider like
Ah,
the reasoning behind
I
that?
just, it's ready to go.
Yeah.
At some point, it's just go.
Sometimes.
Yeah, I get that set up
You
sometimes.
figure it out,
It's
you share the light, like,
Okay.
I do.
We'll try to continue with my sneeze built up in there somewhere. The slightly negative and the slightly positive will interact together, and that's true here as well, all the way around at each location. So water creates an extensive network of what we're going to call hydrogen bonds. Hydrogen bond is a certain type of dipole-dipole interaction. There is a requirement for hydrogen bonding. Here's the requirement. If you have a hydrogen that's connected to an oxygen, a nitrogen, or a fluorine. So this can be anything out here. It doesn't matter what that is in terms of the molecule. It can be carbons, whatever else. But if at some point you have an oxygen and a hydrogen, nitrogen, hydrogen, and fluorine, and a hydrogen, and those hydrogens are binding to, right, another oxygen, nitrogen, or fluorine. So it could bind to the oxygen, it could bind to the nitrogen, it could bind to the fluorine, then you have hydrogen bonding. So notice we have that requirement. We have a hydrogen on an oxygen that meets this requirement, and it's binding to another oxygen that's opposing the side. Just a specific type of dipole-dipole interaction. Water is very unique in that it forms 4 of these hydrogen bonds. The question would then become, like ammonia, could this hydrogen bond in a pure solution of ammonia? What do you think about that? Could that occur? Hydrogen bonding? Yeah, right? It's going to orient itself slightly different though. So if we put the hydrogens maybe a little higher up here, like this, we can get a hydrogen bond here. Then the question becomes, can ammonia hydrogen bond again? Honestly, at that point, arguably, it'd be like, let's look at the empirical data and see if experiment tells us it does or not. For me, what I'd just like for you to know is water has 4 hydrogen bonds, and then otherwise, let's just assume most other compounds that could hydrogen bond can only do so once. That's a safe assumption for us at this level of chemistry. The interesting part of these hydrogen bonds is this. You've had a couple questions that have related to what happens when you throw salt in water. And by salt, we legitimately mean a metal and a non-metal. We do not mean table salt. So we don't mean sodium chloride, a metal and a non-metal. So for instance, if you take magnesium chloride, which is what they throw on the roads, scatter it in liquid form, if you see those trucks with sprayers behind them when it gets ready to snow, that magnesium chloride, if you look at the solubility rules, is aqueous. And behind it, you put this AQ notation. More of this to come. We'll start building up to these ideas later on. AQ means it dissolves in water. So whenever you have a beaker and you have a pure solution of just water, and you drop in a chunk of magnesium chloride, you will not have a chunk of magnesium chloride left over of equivalent mass. That chunk will begin to dissolve. You can heat it up, you can stir it, you can do a whole bunch of stuff to it to make it dissolve more quickly, and eventually you might have some left over if you reach the point of saturation, meaning you can't add any more stuff into there in essence. But when it does dissolve, you get the magnesium ions, and you get 2 chloride ions for every single one of these compounds that dissolves into solution. And then based on the enthalpies of those solutions, so how much energy is going to be exchanged in that reaction, the solution either heats up or the solution cools down. But how does this affect or interact with the hydrogen bonding? We've asked 2 questions. We've said, what happens to the boiling point when you add salt to water? So this is salt. And what happens to that freezing point whenever you add salt to water as well? Let's see if we can kind of tweak this out and try to make sense of it. If you have magnesium ions in here, will those magnesium ions interact with the hydrogen or with the oxygen?
Oxygen.
Oxygen, because that's positive, this is negative. So as this bond begins to stabilize, it actually weakens this bond. Doesn't completely destroy it, but weakens it. And then the stronger this interaction occurs, the weaker and weaker this interaction occurs, right? So now we need to ask the question, what is that doing to the freezing point of water? Whenever you freeze water, do you need all these bonds to be rigid and strong? Or do you want them to be very weak and almost non-existent? You want them to be strong and rigid, right? That'd be a solid structure. So if you add salt to water, in essence, what are you making the phase state of this water become? If this was ice, if it was originally ice and you threw salt in there, liquid, right? And then the chloride ions are gonna be in here as well. As they begin to interact with the hydrogens will begin to weaken their interaction with oxygen, and so on and so forth, until eventually you get a situation where water is really not interacting with itself to any appreciable extent. It still interacts, and you still have the conservation of momentum. Come take physics. Come take physics. Take this molecule, it has motion, collide it into this one. It isn't sufficient enough energy to break that chloride ion off. He'll move to a new side, he'll disrupt this interaction, and this one will have time to rebond. If that wasn't the case, then we should be, in essence, vaporizing the water pretty quickly as well, but it's staying in its liquid form. Okay, so what does it do to the freezing point?
Decreases.
It does lower it, but what does that mean?
It's harder for it to freeze.
It's harder for it to freeze, so you have to remove more energy. And if you remove more energy, then this guy is moving, I'll draw it slow, is moving very slow. And as it moves slow past another water molecule, it might have time to interact and weaken this bond. Think of it as Red Rover, send PD right over, right? You're locking arms. If he's running hauling through there, that's going to be tough for me to grip onto him and say, no, I'd rather be with you than be with this person. But if he just comes casually strolling by, I can reach out and grab him, and in doing so, I can kind of push this other person away because I have time to strengthen that bond. So that's lowering the freezing point. What's it do to the boiling point? It does. What does that mean? How?
It requires more energy to break the bond.
It requires more energy for the water, and I'll draw them as circles up here, not as oxygen. If those water molecules are interacting with these additional ions in solution, and they also still have some hydrogen bonding, then it's going to be very tough to leave the solution because you have to be able to head the right way. You have to be able to head up. You have to have sufficient energy, meaning think of it like legitimately, if I go home and wrestle with my kids, remember how I told you they all lock onto the legs? Like, daddy can't walk. I'm like struggling to just move the legs. It's the same thing. You got to shake off one kid, pound the other one, tickle the other one, and then you can run. I don't kick my kid. Well, not in the sense of like child abuse, right? We just kind of,
Every time
shake
you
them off.
try to justify it, just makes it
I
worse.
don't kick my kids. Well, I give them a good tickle, and they just crimple under the weight of daddy's fingers. Yeah. But you can then escape. It's true. It's true. So you have to have sufficient energy, sufficient direction, and weak intermolecular forces. The other thing that it does is, and I'll draw it like this, if you have magnesium ions and chloride ions at the top of the water, just think of that seriously like leaves on a lake. Like how easy is it for a fish to jump out of, a small minnow to jump out of the lake when it's covered in leaves? It's very difficult. You gotta wait for the wind to blow just right to open a gap for that minnow to jump out of, right? Legitimately, it's the same thing. So it dilutes the surface. There's not enough water at the surface. There's enough water below there, but there's this layer of ions at the top. So it raises the boiling point. We got to get the wind to blow. We got to get those ions to break and ultimately shift their position so things can come out. Okay. All right. So boiling point, hydrogen bonding there. Just as a side note, I think we don't have to talk about it. If you have your DNA structure, what's this backbone made up of?
Sugar.
Keep going. A 5-carbon sugar. I'll draw that as this. It's got 5 sides. Phosphate group. And? What'd you say? It's true. Phosphate group and? A nitrogen containing.
Hydrogen.
Sorry, there was
It's a
this.
nitrogen.
Yeah, nitrogen containing base, like what?
Guanine, cytosine.
Okay. So adenine, guanosine, cytosine, and thymine. All right, I'll just put a few in there. One bonds twice and the other bonds 3 times. I don't remember which is which, so I'm gonna make this up. This part.
I think guanine is
Right.
cytosine bonding.
I don't remember. So these bonds that are in here. So I'll put 3 for A to T, 2 for C to G. We'd have to look it up, but those are hydrogen bonds. They stabilize the conformational shape of your DNA. So when you want your DNA to replicate, you have to cleave these hydrogen bonds to weaken the structure to allow one of these strands to come out here now. Now you add another enzyme that moves in a certain direction that regulates the series that it's going to code for, and goes through the whole process of replication, transcription, translation, etc. So those hydrogen bonds are very important for us in terms of our genetic code. Very good. Very important.
Cytosine and guanine.
How
Have
many?
3 bonds.
They have 3. Dang it.
Like the
Messed that one up. Okay, instantaneous and induced. All molecules have them. Let me draw something that's very big, or relatively big. Is this a polar or non-polar molecule if every single one of those additional attachments are hydrogen?
polar. Symmetrical.
So that makes it
Polar.
makes
Non-polar.
non-polar, yeah, makes it non-polar. This is what we would call hydrophobic, a non-polar molecule. So does it have any dipole moment? No. But in any given moment, is there a net buildup of electron density somewhere? Heisenberg's uncertainty principle says you don't know simultaneously the location and the momentum, which means the direction and the speed of an electron. So if you don't know, then at some moment, there might be a buildup of electron density here. Like some of this density can move this way. That's a possibility. And if it does so, at that instant, that's slightly negative and this is slightly positive. But in the next instant, like legitimately within a billionth of a second to a trillionth of a second, that electron density could shift somewhere else. And now there's a net buildup over here, and this goes back to neutral, right? Instantaneous dipoles. Every single thing has them because we don't know where the electron is at. So you should write yes for this all the time. Induced dipoles are very similar. Let's do a similar structure, not get too crazy here. You just put a few hydrogens. All right, assume those are all hydrogens. If at some given moment you have a net buildup of negative here, what's that going to do to the electron density at that region here? Think about that carefully. If you have a buildup of electron density here, what will that do to here, the electrons here? Attract or repel? Repel. And when it pushes those electrons away, moves this direction, that becomes slightly negative and this becomes slightly positive at a given moment. So again, your proximity of one molecule in proximity to another causes a conformational change. This happens all the time in the hallway. You want to see it? As I move towards Bella, she's starting to get nervous, and if I keep moving, eventually she's going to do this, right? Until I'm all up in her grill leaning over. Yeah, see, there it was. That's the conformational change. Just my proximity. The proximity of this molecule to another one causes a shift in the electron density. So everything has that additionally. Then this one is actually, honestly, what we just did with the dipole-dipole interactions of water. So you don't have to redraw it, you can just go back and label that. If the magnesium ion begins to interact with the slightly negative region of water, then you have an ion interacting with a dipole. That's an ion-dipole interaction, right? So soluble salts in water create ion-dipole interactions. Okay.
So
Yeah.
the endured dipole also happens all the time.
Yes. Yeah, the induced and instantaneous. Yep. And legitimately,
So we put yes, happens all the
Yeah.
time.
yeah, for these two, you're looking for specific situations for the rest. But and it's not your fault at all. It's not at all. If you were to take Chem 3, the very next unit we start with is how fast do these things actually occur. It's called kinetics, the rates at which things occur. And we're literally talking like millions and billions of times a second, these bonds breaking and reforming. This is not a long-lived process. And that's a good thing because when you hit the surface of water, belly flop off the high dive this summer, you experience the full force of those hydrogen bonds. But if they weren't able to break and reform millions of times a second, what would your body do?
Fall right through.
If they weren't able to break?
Oh, you splat.
You would splat, and that's it, right? But if they do break and reform, then you go through the water slowly, and then water produces its, not condenses, but reforms liquid space state over the top of your head. So it's like you're swimming in essence. That's a good thing that happens. However, other times, probably not so much, right? Okay.
Hey yo, question.
Yeah.
How would you like easily so we can write it down the difference between instantaneous and induced?
I would, in my brain, I just go instantaneous, things shift around, electrons shift. Induced is the proximity of one molecule next to another shifts electron density. Okay, this is because I'm going to keep lecturing. Oh, God, Maddie, are you okay?
Yeah.
Oh my gosh. It bounced off the table and hit you in the eye. Are you okay?
Yeah.
Oh my God, I'm a horrible person. Maybe I should keep doing that.
Ow. Give me a warning, hold on.
Heads up. That's your warning. Oh, you guys don't do Jolly Ranchers. You do Smarties?
I'll take a coin.
Heads up. Heads up.
I'm scared.
I know.
Every time I throw candy, do you notice at Davis? Every time she just sticks on her hand like this, she'll just catch it.
It's tennis. I'm telling
She's
you.
literally
Yeah, I poured the other one.
like, here, throw something at me.
What?
Here, throw this at me. But not at just throw something.
I lost that.
Watch. I'm gonna try to do what Davis does. Wait, you gotta be semi on target. Like, aim for here.
I just have
Aim
like
for
different
here. Let me
colors
try.
everywhere so I can tell like what's
Nonchalant.
what.
Did it. You
I'm gonna
nailed
get
it.
that. I'm gonna make my
Every time. You know what I'm gonna start doing? That's what I'm gonna do. Right here. You ready? I'm gonna throw it over there and you gotta catch that. What the heck? She's like a frog, just snaps it out of midair. It's true. Do you see the way they bite it? Oh, true story. Small true story. My mom, we were at a barbecue, and he's an amazing chef. This dude, our neighbor friend, and he cooked grilled crab that he had, I believe, imported just for this barbecue, like fresh crab. Amazing. And we were eating it up. Like grilled crab is, so good.
Side note, is this the Hey Neighbor?
This is a different neighbor. Yeah.
Okay.
I talked to Hey Neighbor the other day. He's like, "Hey neighbor, what you doing?" I'm like, "Digging a hole for my garden." He's like, "Huh? I got a sick kid." I'm like, "All right, we're doing two things here." Anyways, we're eating the barbecue, and we're literally, because it's expensive crab. I'm sure he imported from somewhere. We're like eating the tiny pieces that fall. I believe my dad is sitting across the table and he scoops, you have this special little fork, scoops out a piece of the crab and it catches and he flips it, trying to just get it out. It flies across the table and nobody knows this except me and my mom. And my mom, I don't even know how she did it, she's just picking at her crab, looks up, sees the crab coming, bites it, I kid you not, out of midair, moves her head, grabs it, and just goes back to eating her crab. And I was just like, oh, that's amazing. Seriously. So that's what I think of Davis now. So, at some point, she snatch a Smartie out of the midair. All right, sigma pi bonds. Yes.
Maybe?
Yes. Benzene. Ooh, benzene's a good one. Okay, I'll show this to you on the PowerPoint, but you won't be able to see it quite as well. So let's try to draw it.
Can we 10-minute break?
10-second break?
10-minute break.
You're right. How about 5-minute break? That's fine. Okay, go ahead. Take your 5. I'll wait.
Oh my god. Oh wait.
Fine. No, it's
Okay,
convenient.
well, you got the clock,
Fine.
If you do that, it just makes time slow down, bro. You gotta enjoy the content.
Enjoy it.
Yeah.
You want to go
He
outside?
goes,
Have a
10-second
football?
break?
You want a football?
Yeah,
That's
that's
it.
it.
You want a football?
Okay.
I have a
Not
soccer
playing
ball.
I'm not athletic enough for that.
Yeah, soccer ball. It's a soccer ball. We got one of those.
Maybe I'll punch it.
You have an air compressor?
I do have. I have 2 other ones in here. Actually,
Do you have a cabinet down there, or is it just on the floor
I
like
got
under
this
your
one.
desk?
My dog. She bit it.
I think my dog ate its baseball.
Did she?
Yeah,
She's
she-
like 8.
Yeah.
That's messed up. You should have that dog looked at.
She's also seen part of like a hose?
Oh,
Some other
geez.
stuff.
Better know
I got this one. This one's nice.
Where are you getting those from?
My secret cabinet.
On the floor,
There's
underneath.
See, there I go.
Down in the. Yep, let me in. Let's.
Let me in.
I got a box.
Imagine walking up to someone's house, knocking down. Yep, let me in.
Oh no.
We saw this barbecue driving down the road, and we were coming back from vacation a couple years ago, and we were so hungry. We legitimately almost did that. I was like, kind of joking, I'm like, I'm gonna pull over, and my wife's like, do it. So I started to do it. She starts unbuckling, like she's gonna get out of the car and walk up to this random barbecue and just eat. We were so hungry. We would have been like, hey, Bert, Steve. How do you guys know them? Oh, you know, let me get you something. Can I get you something? You know, and just play it off. It wouldn't have worked out. It would have been bad.
It could have.
I don't know though.
They could have been nice people.
Some people would be like cool with that, like.
Yeah, that's also how you get shot though.
That.
True.
Okay, it depends on the neighborhood, I
take the
guess.
risk,
Like,
I mean,
if you
nice.
look for the town.
And barbecue or
Yeah.
shot occasionally, 6 times, 7 times.
Nobody.
I mean-
Nobody who has a gun is gonna.
I was also driving to the country and this cow was on the road. And I looked at his brand, backed up, saw the farmer. He had his brand on his mailbox. Like, that's his cow. So I walked up, this is sketch. Almost night, me, sunglasses, hat, towering fortress of a man, right? And I was walking down this long, probably 100-meter-ish, maybe a little less. Yeah, probably a little less, but road, where the whole time I'm walking, because I parked my car at the end of the driveway, I wasn't just gonna pull up in his house. So I'm like, this is it, this is how I'm gonna get shot. It's sort of like 50, 60 meters, I'm like, this is it, anytime, the bullet's gonna come. I'm like, I'm just walking up to this guy's house. And then he does one of those like peeks out the door, and I'm like, he's got a gun, he's got a gun. I'm like, hey man, your cow's out. He's like, oh, thanks. We had a good conversation, that's literally all we said. So I was like, I think there's a cow on the road. He's like, I'll get it, thanks. Alright. I'm gonna walk away, don't shoot me. I was like, walk away now. Fortunately, yeah. Peabody, Kansas. That's where
Unfortunately, he didn't
No.
shoot. Or.
No, fortunately.
Oh.
Yeah,
I thought you said unfortunately. I was like, I mean.
Yeah.
There was a shooting at Lake East High
Recently?
like 2 weeks ago. I did not know that. I had to learn about this through TikTok. And it was from the perspective of a student, and I was like, what?
Awkward.
Because I was looking through the comments, and then, because I thought like maybe it was like a drill or something,
Yeah,
and they were like, only in Kansas, and I was like, this wasn't in Kansas.
yeah.
Luckily,
Daughter.
3 people were shot, but they were all okay. But now the kid that like brought it is being charged with capital murder, or attempted capital murder.
It's so sad. Goddard had one almost 40 years ago.
Oh, you know
Out of
how I
high
found
school.
out about that one? I was reading a book, and
Really?
at the end, I don't remember what the book was about, but the very end of the page, it was like the earliest like school shootings, and Goddard was like the top one, and I was like, oh, well, that's interesting.
I think the principal was shot, an athletic director killed, or maybe the other way around.
Yeah, there's a bell over there.
Yeah,
too,
it was one of those. I think 2 people were shot and 1 died. One principal or teacher or somebody. That's crazy. Goddard, Kansas. 35, 40 years ago. That's crazy.
35, 40 years ago, there was a lot of stuff going on.
That's true.
That,
Yeah, there was a lot of stuff going on,
That's
Mr.
like-
Morgan.
that's true. What would that have been, like 2000? 2001?
35 years ago.
You said 40 years ago?
Probably, bro.
Just
Uh,
take
in like
You
1980.
guys take your
Yeah.
birthday and go
I
back 5
would have
years.
been little bitty Blake. Little bitty. I would have been,
I thought you're 35.
yeah. So I don't know if I was born yet. I was probably this big.
Oh my god, there's a 5-year difference, dude.
Yeah, you're right. Maybe I wasn't even little bitty. Maybe I wasn't.
I mean, technically, you would be very, very,
Yeah.
very.
And
It's
split
true.
in half.
Yeah.
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 Yeah, I agree. I would have been tiny. Try teaching a 7-year-old, because we're trying to, about that babies don't actually live in mama's stomach.
I mean, technically they do those.
I know, but they think you eat and baby grows.
But yeah,
Inside
that's
is
how it
something.
works.
But
You eat and then
you
it
see what I'm
feels
saying? It's like the baby's not getting the hot dog you just put down, and you know, it's not like having to push the
That's
hot
true.
dog out of the way. It's like it's not the same thing.
You're not living in your stomach.
It's not.
I
Yeah.
mean, we told my brother how it works. Like, there's like a
Yeah.
separate pouch for the baby,
Right.
and it's not like a stomach.
That's
and he
if
was
you
like,
use
"Oh, okay."
A pouch. I haven't tried the word pouch.
Like a kidney pouch. You
Yeah.
know? It's like a little.
well, that's kind of what it is.
Except it's flush.
I haven't tried
There's a
pouch.
separate area. in
It's
there.
just inside
Yeah.
instead of outside.
Yeah. Huh.
And then
These
my
internal pouch.
parents, whenever I was asking, said that that like a little bit of everybody was a part of me.
Yeah.
Ew.
So trying to do the genetic code, huh?
Oh, that's weird.
Yeah. She went the genetic route. She's
I
like,
don't know if my kids are ready for that yet. Yeah,
I don't think I want my
see,
mom
but I
telling
was
me
like
that.
7, and
it's
this was
party.
a phase where I was
Yeah.
looking at YouTube videos with birth and
Yeah,
everything.
Right.
That was
Well,
strange.
I mean,
I am.
I don't even know
Papa.
someone
What are you
has
saying?
at least it wasn't TikTok.
I don't do that.
Oh, TikTok's kind of.
I was born in the 1900s. I really don't know what you're talking about.
Okay, let's be honest. Who had music?
I was
videos?
terrified.
There's fucking flies everywhere.
I know.
Oh, yeah,
There's
you're-
so many.
I know.
I
It's
know.
true.
They're over
Not
here.
allowed to have
That's
anything.
Have you,
I mean,
sometimes you
scrolling
should
down
look
my
at like this
TikTok all
stuff.
the way back to like 2017.
Fertilizer.
Terrible.
It's not fertilizer. Bag of soil
Terrible.
I used. All right, let's do this.
I really don't want to.
Let's do it.
Me neither.
Rainy sleep. It's rainy. It's nice. There's a weird.
It's only
shape.
day 2 of us being back at the school.
I know. I love it. We have so many opportunities. All right, so this is benzene. It's found in the air. It is cancerous causing. You can't get away from it. It's in a small proportion. You're just around it your whole life. Not a big deal. However, it is kind of the backbone, if you will, of many, many different types of chemical reactions, including the kind of looks like, and it's not always, benzene's not, but it looks like similar to a steroid. If you've seen, don't draw this, but if you've seen general structures of some types of steroids, they can look something like this. Honestly, your guanine, adenosine, and cytosine in uracil also have this general backbone structure as well, depending on whether it's this or whether it's just this or that, right? Okay, so this is benzene. We're eventually going to name this. This will be a cyclohexane structure. If we go ahead and draw in the Lewis dot structure, eventually it would take some time, probably about 10 minutes, but we could get here. So this is the overall structure of benzene. Does this have resonance? Resonance.
Nope.
What do you think?
Oh, wait, are those double bonds?
Oh, I didn't tell you.
Are those
Sorry,
double
everywhere
bonds?
there's 2 lines connecting, that's a carbon. So everywhere there's 2 lines connecting, that's a carbon, unless you see something else there.
And so those are double bonds.
Those are
Okay.
double bonds, yep.
Then yes.
Yeah, you have resonance, right? Because you can shift these bonds around to these locations and create what's called an aromatic compound, something that has resonance that's distributing the electron density other ways. All right, let's try to figure out which ones are sigma and pi, as well as any hybridization occurring within the molecule itself. Okay. All right, so maybe what's the easiest point for you? I don't know. It's a question. Do you want to start with sigma, pi, or hybridization? What's the easiest? Sigma? Okay, what is sigma? Single bonds, okay. So we know this is sigma, this one's sigma, right? We have sigma here as well, and sigma, right? So single bonds, sigma. That would be the internuclear axis connecting this carbon and this carbon, lying in the same plane, and that's a sigma bond. What are the double bonds?
Wherever carbon meets hydrogen.
Pi bonds.
Those are pi, okay. So we have 3 pi bonds, right? And those are perpendicular to the internuclear axis connecting those. So what, in this scenario, what direction would those pi bonds be pointing? If this board literally represents the plane that these carbon atoms are all binding to, which direction are the pi bonds?
Left to right.
What do you mean by left to right?
Like, kind of like.
So,
kinda
yeah,
like this.
okay. So if this plane is like this, we do have a x component and we have a y component, so that's our 2-dimensional plane. Our 3rd dimension would be here, our z component. So these pi bonds are actually sticking out like this out of the board at you, and then they're overlapping to create some electron density here. Okay. So kind of cool. All right, hybridization. What about all the hydrogens? Are they hybridized or unhybridized? Yep, those are what atomic orbitals? 1s. Because hydrogen only has one electron in the 1s orbital, and how many times can hydrogen bond? Just one. So there's no need to hybridize hydrogen. Okay, now we need to look at the electron pair geometry at this particular carbon. How many regions of electron density surrounding that carbon? 1, 2, 3. That double bond counts as one region. So what's the hybridization of this carbon? So is that trigonal, planar, tetrahedral, or linear? That's trigonal planar, so that's sp2 hybridized. We easily, not easily, but we could say this is one of those sp2 hybridized orbitals. How many of them do we form for carbon? 3. So we have sp2, sp2, sp2. Okay. How do we know there's 3? One atomic orbital plus 2 atomic p orbitals creates 3 hybridized orbitals. That has to be 3. If you take 3 atomic and mix them, you create 3 hybridized orbitals. Here's the second one. Where's the third one? Okay, here. So we could say one of the sp2 hybridized orbitals of carbon is interacting with the 1s atomic orbital of hydrogen to create a covalent bond. That's how the language of that would unfold. What would you say here? What's this interaction? How would you use words to describe that covalent interaction? So it's true, it's signal. So let's say one of the I'll shade as I talk, one of the sp2 hybridized orbitals of carbon interacts with the other sp2 hybridized orbital of the other carbon to create a covalent bond along the internuclear axis, resulting in a sigma interaction, or a sigma bond, right? And you could keep doing that and doing that and doing that over and over again. What about this double bond? How would you describe that? What words would you use? One of the unhybridized atomic orbitals of carbon, from which sublevel? 2s, 2p, 3d? So this would be
2p.
an unhybridized 2p atomic orbital from carbon interacts perpendicular to the internuclear axis with what? What's it interact with? Another unhybridized 2p atomic orbital of carbon, right? So those are identical. And that's it. I mean, legitimately, there's a ton going on there, but you really only have 3 things occurring. You can have an sp2 with a 1s interaction, sp2 of carbon with an sp2 of carbon, or you can have the pi interactions. And that's it here. What's that?
Can you scroll up on the slide?
Yeah, absolutely. So the pink showing the interactions perpendicular to the hardest. This is blue, and that's sitting like this in the board, and these interactions would be sticking out at you.
So it's the same thing as earlier we saw, right?
Hmm?
Where it was like
Yeah.
going like left or right of
Yep.
it or up.
Yep,
So which one does it go? Does it go up and down first or like left or right?
Honestly, just, and to your point, maybe I'll answer that indirectly and then directly. It would be, ask a question, do these molecules, take this marker, if that's a molecule and it has this shape, does it move through this room like this? Does it move like that? Take a guess. No. It's this in 3 dimensions, right? Constantly up and down, it doesn't matter. So at any given moment, your good question is, does it go left or right? Does it go up or down? It could be any direction. It matters which direction the molecule is pointing at the time you take the picture. So at the time you take the picture, this is the plane, then we should be going like this. So I'll just keep my thumb here. If in this moment, the molecule's like this, right? Like this, right? In 3 dimensions, just always keep it perpendicular. It doesn't matter how it rotates in that plane. There's something called the right-hand rule. in organic chemistry. But we're not. We're not.
We got told what it is.
It's that. It's in essence, if you have a molecule and there's stuff binding on there, if you take your right hand and you curl it, in the order, you'd have to prioritize these groups attached. And if you curl it in a certain direction, the direction your thumb is, tells you about the rotation of the molecule and whether it's going to polarize light, deflect light to a certain degree. Kind of cool. Okay. Now we're ready. Now we're ready.
I still
No,
don't
we're
understand
not.
anything.
We're here.
I'm honestly
No,
very
like my
confused
brain is
about
still
what.
trying to comprehend
you
everything
just
we've already
did.
taken.
Yeah, we're
I still
gonna.
don't even understand hybridization, so
Yeah, I don't either.
yeah.
Yeah.
So we're
Yikes.
Oh well, no. 1s and 1p hybridize to produce. So these are atomic. So can I write a plus sign there? Or a plus. S and P hybridize to produce SP and SP.
So it hybridizes to like open up some like
A bonding
so that it only
position.
has one electron, right?
Yeah,
so
hybridizes
that's
to
like
open up
open space?
an orbital to allow another electron from opposing atom to bond to it. So this would be linear. If you have S plus P, that's 3 atomic orbitals. You create sp2, sp2, sp2.
What?
So this is 2 atomic orbitals. 1, 2. 1, 2, 3 creates 3 hybridized orbitals. Keep this as linear. Keep this as trigonal planar. And the other one is tetrahedral. So S plus P plus all 3 P sublevels, if they hybridize with the S, then you create sp3. But how many times? 4 times. 4 times. 1, 2, 3, 4 atomic orbitals produces 4 hybridized orbitals. So in essence, the number of orbitals is a conserved quantity for our purposes.
Did you have a quiz over this?
Yeah, but in essence, that's it. That's it.
Yeah.
No, I just mean, everything we've done literally culminates to just this. If you know the orbital diagram doesn't work, you can't add any more electrons in, then you should consider hybridization. Based on the molecular geometry, you know what the hybridization is.
But I don't.
Yeah, go ahead.
I don't know. I don't understand any of the shapes. The shapes are really.
These
hard to
shapes,
see.
is that what you're saying?
Yeah.
Yeah.
Okay.
Those are the molecular.
Yeah, those are, yeah. Those, but in terms, let me rephrase that. In terms of understanding these shapes, I think looking at a 3-dimensional structure online is probably a better option than trying to draw it on the board. If we took this one, what shape is that? That's tetrahedral. 3-dimensionally on the board, we haven't, we mentioned it, but it's not necessarily something I need you to do. Would be this. So this carbon I'm holding onto, this one on the side. If you were to look at that, I could chop those in half with my hand perfectly. So that means they're in the same plane. This is the plane that they're in. This one sticks in front of my hand. So this would be what we draw as a wedge. And this one sticks behind my hand into the board, it's a miscellaneous room, and then we call that a dash. So not easily visualized in 2 dimensions, right? That's how scientists would do it. So arguably, if you can find something like this online that can animate and or rotate the object, that'd even be better. Maybe Khan Academy, I haven't looked to see if they have any
No.
3-dimensional stuff. You've looked, no 3-dimensional stuff on there? Yeah. Okay. All right, let's, we can keep coming to that. We can tie that in. Let's go molecular orbitals.
So when's our quiz?
Oh, you know,
Tomorrow.
at the end of the app. No, I was kidding.
Oh my god.
No, you will practice before you have a quiz. All right, so let's do potential energy on this axis. The x-axis doesn't matter in terms of orbital diagrams. Remember, we're doing the same thing. 1s.
So this molecule. How big should this be?
Half the page. So we don't need a whole.
Sure.
Just, you don't need a whole sheet yet, just so.
Well, I'm getting a new section for it.
Yeah. Alright, let's predict, let's do a prediction of what the molecular geometry of homonuclear diatomic molecular oxygen looks like. Pair unpaired? Now what?
Carrot again.
Paired again. So this should look like a double bond. Alright, that's a prediction. That doesn't mean that's what occurs. Let's calculate the formal charge. Formal charge here.
That is so pretty.
6 minus 1, 2, 3, 4, 5, 6. 0. We could develop something where we had this, right? What's the formal charge here? This would be -1. What's this one? 1, 2, 3, 4, 5. That's +1. That still lets you go neutral. We could come up with probably another option, right? We could shift the electrons this way. We could put a triple bond in there, so on and so forth. Okay, so we have lots of different options. Which one is actually contributing more? That's what the molecular orbital diagram is going to help us understand. Okay, so this is, I'll just put oxygen down here and oxygen down here. We're going to do the individual orbital diagram for oxygen and oxygen. And then we're going to combine them together into a molecular orbital diagram. Okay. All right, so oxygen's electron configuration, 1s2, keep going.
2s2, 2p4.
Okay. And this is just for oxygen. And then I'll try to be careful about the heights of these. So the 2P's should be at the same level. The 2 S's should be at the same level.
Should they all be on top of each other?
For this, yeah, it's just simpler. Remember, and not our point today, but remember the further away you go from the nucleus, the closer and closer and closer these energy levels get. Not our point today though. Okay, if I have the internuclear axis, I'll call it Z, and I put an oxygen atom here and an oxygen atom here, can they bind along this axis? Can they share electron density and overlap along that axis? Is that a possibility? And if they do, is that a sigma bond or pi bond? Okay, so we have a situation where this occurs, there's overlap, that's sigma. So let's go ahead and put that in here. We have a 1s, sigma 1s option. Okay, so something like this. So subscript 1s, sigma 1s.
So
Notice the energy, what's that?
it's lower than.
Yeah. Notice the energy of the 1s is lower than the energy of either of the 1s atomic orbitals. This is a molecular orbital. Why? Why is this lower in energy than either of the unbonding atomic orbitals?
Just bonding together and not sharing.
Bonding, yeah. Bonding, whenever a chemical reaction forms, you release energy. Always. 100% of the time. Now, did you release a lot of energy or a little bit? That's a different question, but you always release some amount of energy. So more stable to be together than it is to be apart. Okay, is there a situation where these two atoms, let's say this very carefully, if we can never do this in Gen Chem, never. Is the electron a particle?
Yes.
Is it a wave?
Yes.
Okay, if you have, don't write this down, but if you have a wave and you have another, oh man, physics, and you have another wave that looks like this, is that deconstructive interference or constructive interference? I've never told you, I'm just curious. Deconstructive because the amplitude of this wave and the amplitude of this wave, if you add them together, what's the result? It cancels out and it's along that flat line, right? That's not a good thing for two electrons when they're deconstructively interfering. Constructive interference would be the opposite. If you have ground wave and the solid line interacting together, what's the overall result here? You get a bigger wave, and that's constructive interference. Constructive interference in chemistry lowers the potential energy. That's this. This is the constructive interference of two overlapping wave characters here. That's a covalent bond, constructive interference.
So,
So that's brown. That's the brown and the solid line interacting together. The two peaks make a resulting wave that's even bigger than what was before.
but it's not always constructive interference, is it?
Right. So now we have a situation where what happens if the electron is deconstructive interfered? Is that a bonding situation or not? And that's a no. So deconstructive interference means these two atoms are in proximity to each other, but they're not interfering. They're kind of pushed, the densities are kind of leaning back and away from each other. Is that still occurring, deconstructive interference, along the internuclear axis?
Yes, but not
Okay.
as much as.
Anytime you're along the internuclear axis, you call it sigma. This is still in the first energy level. And now we put a star here to say deconstructive interference. That's called sigma star. That's how you're going to say it, sigma star. And that's called antibonding. So non-bonding situations. So you have two options. You can either bond along the sigma axis, or you don't have to bond along the sigma axis. Does that make sense?
So is it just random whether or not the electrons interact?
No, we'll fill them in. Hold on to that thought. Let's keep outlining, then we'll come back to that. What about the 2s? Does the 2s, does it have a sigma axis? This 2s atomic orbital. So now if I draw a larger sphere, that would be 2s. 1s is a tiny sphere. Could those interact along the sigma axis? Yes. So we have a sigma option. Why is this sigma 2s higher in energy than the 1s sigma?
Because
Further
it's
away.
second energy level.
Yeah, it's second energy level, it's further away, so it has to be higher up. Why is the sigma 2s greater in energy still than the 1s? That's not as intuitive. So this non-bonding situation is still more stable than a bonding situation that's higher in energy? Yeah. Does it always like that? Probably not, the further away from the nucleus you get, because those energy levels start to get closer and closer together. Is there a sigma star option?
Yes.
Yeah, because now you could have these two big circles non-bonding along the internuclear axis. Yeah.
So it has the sigma and the sigma star because it could be constructive or
Yes.
it could be deconstructive.
Now do the same thing, but instead of talking about the internuclear axis, go perpendicular. We cannot go perpendicular on the first energy level. Why not? Why can we not say there is a pi bonding situation for the first energy level?
Because there's only one shape that you can say.
There's only one shape, and it's S. There's no P's, right? So second energy level, we can pick up pi bonding because there's a P sublevel shape. Okay, so let's draw that. So here's the internuclear axis. Here's the P shape, right? I did a horrible job of that, but pretend like that's a teardrop. Can those two bond together constructively? So what would you call that then?
Oh, the sigma bonds.
This is a sigma. I ran out of space. Don't worry, yours is, I'm sure, so much higher up than mine, right?
No.
Dang it. I'm writing big. Sigma 2p, right? They could be bonding together, and which also means there's a sigma star as well, right? Non-bonding situation. Now that non-bonding, if you're looking at it, remember the bonding occurs lower than the atomic orbital, the non-bonding occurs higher than the atomic orbital. So our sigma star is somewhere up here as well. So I'll put it up here for now. Maybe don't write yet. Don't write the sigma star. There's gonna be some stuff in here. Just let me get it all on the board and then you can go back. I'll give you a time to write that. Sigma star 2p. Now, can we take these two shapes and orient them perpendicular to the internuclear axis? Is that a possibility? Can you take these shapes and put them perpendicular?
No, because then it won't be bonding at all.
Well, yeah, we can discuss that in a second, but could they go perpendicular? Okay, so if they're on the internuclear axis, they're sigma. If they're perpendicular, they're if they're perpendicular?
They're
Pi.
not, right?
Pi. They're pi. Sigma is along the line. Perpendicular is pi. If they interact, perpendicular, is that pi or pi star?
Pi star.
If they interact,
Oh, pi.
that's pi.
If they don't interact.
And if
then
they
it's
don't
pi star.
interact, that's pi star, right? So you have options there. Yeah, go for it.
So it can't be, so the S sublevels can't be pi bonds
Right.
ever?
Right.
Because they're circles.
Because it's a circle.
Okay.
No, there's only one orientation is what we say, not because it's a circle, but only
Yeah.
one orientation, which happens to be a circle.
And
Okay.
so, if, I'm sorry.
Yeah, go here, go for it.
No, you go first. No, you go
Okay.
first.
Oh,
No,
you
you
go.
go.
Go at the same time, go.
No.
All right,
No, you go.
Akira, go for it.
Okay, so the stars are the deconstructed, right?
Yes.
Why is the potential energy lower? Because, like, I'm thinking of it with the waves and everything, like,
Yeah.
constructed, they make it bigger, so wouldn't
Yeah.
it be bigger?
That's because you've taken physics. That's the problem. No, I'm serious. Yeah, because in physics we teach it the opposite, which is two waves that come together increases the energy of the resulting wave.
Yeah.
Yeah,
Okay,
but
so
this
what
is
are
chemistry.
these waves?
These two waves when you do constructive interference, that means they're entangled. The electrons like the behavior of the other wave.
So,
So
so
they're
it
bonded.
lowers, so they're bonding, so it lowers the potential
Yes.
energy.
Oh,
Because
okay.
when they're
Yes.
rejecting each other, they have a higher
Right.
potential energy too.
Right.
Okay.
So, and that, what you're looking at, and it's deeper than I even know. The simple level that I would be confident saying is when you have wave character of an electron this way, and its properties are different than the properties of this incoming wave, they don't like that. They like the properties to mimic so they can entangle, share the electron density between them. And that's the deconstructive. In physics, again, we teach the opposite, which is two incoming waves, increase the amplitude, increase the energy. But that's a different situation. Those are mechanical waves. This is not a moving wave. Does that make sense? Like an ocean wave is mechanical. It moves. The water actually moves. The electron is not moving along a wave. It is the wave. See the difference there? Not a boat on the wave. It's the actual wave itself.
Oh.
That's why we can make a distinction between the physical reality of mechanical waves.
Wait, I need you to repeat that. So
Yeah,
electrons
Not
are
the same as physics. So let's do this. Okay. So here's what we said. These two markers can sit perpendicular, and if they do, they can overlap. Now watch this. That's one. Can these markers sit like this and overlap? Is that still perpendicular?
Yes.
Yes. So you have one orientation, and you have a second orientation. That's these two. This one could be coming out at you. This one could be going up.
Okay, so that was my question earlier. Does it matter like which way is perpendicular? Like
Yeah, we'll make this Z, since we've labeled this axis Z. So PX, PY, PZ. PX, PY, PZ. Same thing here. So if this is PZ, what's this and this?
EY and PX?
Yep. PY or PX and PY. So PZ bonding, that would be here. PX bonding, PZ bonding would be here. PX bonding would be perpendicular here. And PY bonding would be perpendicular but here. Now do all three of those situations, but instead of bonding here, do non-bonding. And instead of bonding here, do non-bonding. And instead of bonding here, do non-bonding as well. So we should have pi star and pi star, 2px, 2py, and pi star, 2pz. Take a guess why non-bonding along the sigma axis is more unstable than non-bonding perpendicular to that axis.
because it breaks the rest of it.
What do you mean?
So
Maybe.
if it's deconstructive along the signal line, then the pi lines can't form. I assume.
Yeah. Whenever you're perpendicular, remember it was a horrible analogy yesterday, but I tried it. Remember I said tug of war you're between two people, but take one of the strands of the rope, still hold on to this one, and play tug of war with somebody up here. Remember that poor analogy? But that's already weaker because the vectors, the force that I'm applying, the vector this way that I have to apply a force to, that's different than the force that I can apply this way. So in essence, what we're saying is, if I have to now have this entire person who wants to be near me, the electron, and I have to push them away, that requires a huge amount of force because you're right here, every part of me is vector oriented to push you away this direction. Whereas here, you already are weak interaction, and I can just be like, snip,